Assalamualaikum warahmatullahi wabarakatuh. We are from Group Kimchii. Today we are going to present about audio equalizer for music using digital signal processing under the subject ECC 3952 Digital Signal Processing. My name is Wana Husna binti Abdul Halim and this is my partner Nurul Ili Khadijah Hanis binti Zaki. Let me give a brief introduction on this project. Audio equalizers improve sound quality by adjusting different frequency components of an audio signal. Since music changes over time, it is important to analyze it in both time and frequency domains. We choose the song Let It Go because it clearly shows variations in pitch, loudness, and intensity between the intro and chorus. A spectrogram in MATLAB was used to observe frequency components over time. Based on this analysis, a three-band digital equalizer was designed using Butterworth IIR filters due to their smooth frequency response and efficiency in real-time applications. The objectives of this project is to apply engineering knowledge and research-based methods to solve complex problems, including experimental design, data analysis, and interpretation to support accurate conclusions. And next is to communicate effectively in engineering activities through clear reports, documentation, and presentations for both technical and non-technical audiences.
Hi and Assalamualaikum everyone. So my name is Nurul Ili Khadijah Hanis binti Zaki. My metric number is 223903. So for my part, I will explain about part 1, which is time frequency analysis and feature extraction of a music signal. Okay, so for the first part is part 1, which is the spectrogram for low pitch, which we use the introduction of the song. So the graph show the low pitch introduction section, which illustrating the distribution of frequency components over time. So a spectrogram provide a time frequency representation of the signal where color intensity correspond to the signal energy. So the horizontal axis represent time, which is seconds, while the vertical axis represent frequency, kilohertz, and the color scale indicates signal magnitude with warmer colors, yellow and green, denoting higher energy, and cooler colors, which is blue, indicating lower energy. So from this figure, it is observed that the intro of this song is dominated by low frequency components. So with strong energy concentrate below approximately 5 kHz, this reflects the low pitch nature of the intro, where bass tones and lower musical elements are more prominent. So in contrast, higher frequency components are relatively weak as indicated by the predominance of cooler colors at higher frequency. So now we move on to the spectrogram high pitch chorus. So for this graph, it presents the spectrogram of the song's high pitch, which is the chorus section, where it illustrates how the signal frequency components evolve over time. So the spectrogram provide a time frequency representation where color intensity correspond to the energy and magnitude of the signal. So like before, the horizontal axis represent times, which is second, while the vertical axis show frequency, kilohertz. So the color scale indicates signal strength, with yellow and green regions representing high energy levels and blue region indicating lower energy. So from this figure, it's evident that the chorus contains strong and sustained energy across a wide frequency area. So significant energy concentration appears in low to mid frequency region below approximately 6 kHz, which correspond to dominant musical component such as vocal and instrument accompaniment. So in addition, noticeable energy is represented in the higher frequency region, reflecting the high pitch characteristic of the chorus. Now we move on to the next part, which is the frequency spectrum for low pitch, which is the introduction of the song. So this illustrates the frequency spectrum of the low pitch section of the song, which obtained through frequency domain analysis. So the frequency spectrum show how the signal's power is distributed across different frequency, allowing dominant frequency components to be identified. So the horizontal axis represent frequency, while the vertical indicates power magnitude. From this figure, it can observe that the signal exhibit its highest power at very low frequency, with a peak occurring at approximately 0.26 Hz. As the frequency increased, the power level gradually decreased, indicating reduced contribution from higher frequency component. So a sharp drop in power is observed beyond approximately 11 Hz, after which the spectrum remains relatively flat at a low magnitude. So the behavior suggests that the majority of the signal energy is concentrated in the low frequency range, which is characteristic of a low pitch musical section. So now this figure show the frequency spectrum of the high pitch section of the song, which is the chorus part. So this obtained through frequency domain analysis. The frequency spectrum illustrates how the signal power is distributed across different frequency components, enabling identification of dominant frequency range. So like before, the horizontal axis represents frequency, which is in Hertz, while the vertical axis indicates power magnitude. So from this figure, it can observe that the signal contains significant power at low to medium frequency, with most of the energy concentrated below approximately 11 Hz. As the frequency increased, the power gradually decreased, which this figure show which this graph show a sharp drop in the power is clearly visible after around 11 Hz, beyond which is the spectrum remains relatively flat at a low
Let me
magnitude.
explain about part 2, which is equalizer design. To equalize the audio, we use the FIR and IR filter. For the IR filter, we use the Butterworth bandpass IR filters during the analysis stage due to their small frequency response and low computational complexity, which making them suitable for separating bass, mid-range, and treble components efficiently. For the FIR filter, we use the window method with zero phase filtering because it is stable and linear phase response. The FIR filter we use for the real-time GUI equalizer. For the frequency band selection, we use for the bass 20 until 250 Hz, mid-range 250 until 4000 Hz, and treble more than 4000 Hz. And the cut-off frequencies are normalized to Nyquist frequencies. These bands align with human hearing perception, so the cut-off frequency were normalized for proper digital filter design. So next is the real-time GUI based equalizers where the users can control bass, mid and treble gains using sliders. Any adjustment is applied instantly to the audio output as well as to the time domain and frequency domain plots. This allows real-time interaction and immediate feedback. Next, I will explain about the frequency domain changes. In the slides, it will compare the frequency domain's behavior before and after equalization. Before equalization, the signal shows a natural energy distribution. Meanwhile, after equalization, energy is increased in the selected frequency bands, demonstrating effective and controlled frequency enhancements. In the picture, it shows when the treble is on and when the bass is turned on, and lastly is when the mid is turned on. It shows the output is differently when each of the band is turned on. Next, the spectrogram results. It will show the before equalization and after equalization. It shows the natural energy distribution before the equalization, while after the equalization, it will increase the energy in the boosted bands. In the frequency domain results, before equalization, energy is mainly in the low and mid frequencies. After equalization, the spectrogram shows control enhancement in selected bands, confirming successful frequency shaping without distortion. In this slide, it further emphasizes the comparison between the original and equalized spectra, highlighting how the equalizers selectively boost desired frequency components with the stable and balanced output.
Now I will explain about the part 3, which we need to record our voice to signal playback and integrity verification. So now for the first graph in part 3, it shows the recorded voice signal in the time domain, which representing how the signal's amplitude varies with time. So the horizontal axis indicates time in second, while the vertical axis represents signal amplitude. So from this figure, it can be observed that the waveform contains varying amplitudes corresponding to changes in speech, loudness, and articulation. So regions with higher amplitude indicate stronger vocal energy. So while lower amplitude region correspond to poses or softer speech. This time domain representation reflects the non-stationary nature of human voice signals, where amplitude changes continuously. So for this part, this figure show the frequency spectrum of the recorded voice signal. So this graph obtained through frequency domain analysis. This spectrum illustrates how the signal power is distributed across different frequency components. So the horizontal axis represent frequency in hertz and the vertical axis show power magnitude. The spectrum indicates that most of the signal is concentrated in the low frequency range, which is typically of a human speech. As frequency increase, the power gradually decrease, with a noticeable drop beyond the higher frequency range, indicating minimal contribution from higher frequency components. For this part, it shows the spectrogram of the recorded voice signal, illustrating how the frequency content of the voice varies over time. So, from this spectrogram, it can be observed that the recorded voice signal contains strong energy concentration at low frequency, which is characteristic of human speech. Energy is also present at medium frequency due to vocal harmonics and articulation, while higher frequency components appear weaker. The vertical patterns across time indicate changes in speech sounds, such as syllables, consonants, and pause. So the spectrogram confirmed that the recorded voice signal is non-stationary, with frequency components and energy level changing continually over time, which is typical behavior of human speech signals. So for the discussion, this audio analysis of Let It Go from Frozen reveal a clear spectral difference between the intro and chorus section. The intro is dominated by lower frequency components with lower energy, while the chorus show a high energy across a wider frequency range. So this observation supported the use of equalization for targeted frequency enhancement. So the design equalizer using FIR filter with linear phase response provided stable and distortion-free performance with visual analysis closely matching the perceived
In
audio.
conclusion, this project successfully analyzed an audio signal and designed a functional digital equalizer. Time frequency analysis revealed and revealed the spectral characteristics of different musical sections, enabling effective frequency band selection. The use of IIR filters for analysis and FIR filters for real-time implementation ensures stable performance and high audio quality, while the GUI-based equalizer demonstrated practical and intuitive control for audio enhancement applications.